Alright. Alright. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon, everyone. So today I would like to continue our lecture session, which is in chapter 4.4, and we are going to proceed with chapter 4.5 after this. And for the second part of our lecture video, I will explain to you about chapter 5.1. So I will make two different videos for this week's lecture so that you can watch it like separately and not really because I don't want to combine a different chapter in one video, so I will make a separate video of it. Okay, so now I'm going to continue what we left last week. So last week we just have a brief introduction on what is hydrogen bonding. So as you guys know, what is hydrogen bonding? So hydrogen bonding is the attractive forces between the hydrogen atom that is covalently bonded with the FON atom with another FON atom of another molecule. So that is what hydrogen bonding is. So this hydrogen bonding has a very significant effect on the physical properties of the molecules, which are boiling point, solubility, and the density. And the density, we're going to focus on the difference in density between water and ice. Okay, so now let's look at the relationship between the hydrogen bond and the boiling point. So hydrogen bond is stronger than the van der Waals forces, as we all know. Alright, because the difference in electronegativity between the hydrogen and the FON atoms makes the bond more stronger than ever. Okay, and it's really high energy to break the bond between the molecules. Okay, so since hydrogen bond is the strongest intermolecular forces, it will make a really drastic difference between the boiling point among the other molecules, and it causes higher boiling point. Okay, so because much higher energy needed to break the hydrogen bond in hydrogen bonding before the molecules can separate and enter the gas phase. Hence, why the molecules that can form the hydrogen bond tend to have higher boiling point than the other molecules that just have the van der Waals forces between the molecules. Okay, so if you can see this example, there is this picture shows the hydrogen bonding in ethanol, where as we can see here, there is the hydrogen bonding between the hydrogen that is covalently bonded with oxygen and the oxygen of another molecule. Same goes to here. This oxygen has been covalently bonded with hydrogen of another molecule that is covalently bonded with oxygen. Oh my god, it is such a tongue twister. Okay, so so this is the hydrogen bonding. Okay, so these two are the hydrogen bonding. Okay, alright, so we want to look on what is the effect of the hydrogen bonding on boiling point. We are going to look at group 14, group 15, 16, and 17. As you can see, in group 14, these are most nice trend, because it follows the trend where going down the group, the van der Waals forces increases. That's why the boiling point increases from CH4 to SNH4. However, when we look at group 15, group 17, and group 16, there is such an anomalous case happen here, where the water, HF, and NH3 molecule tend to have the highest boiling point among the other molecules in their respective group. They do not follow the trend increasing in order. They suddenly have the highest boiling point and then going down, and then they move into the trend just like usual. So that's because these three molecules all have the hydrogen. Bond. So that is why these three molecules have a relatively higher boiling point than the other molecules in their respective groups. Okay, so let's see. So let's see the explanation here. So in group 14, the CH4, SiH4, GeH4 and SnH4, they display normal behavior because hydrogen bond is not present in all molecules in this respective group. So the type of intermolecular forces exist between the molecules are only the van der Waals forces, Okay, so the boiling point will increase regularly when the relative molecular mass increases. So when going down the group, the molecular mass increases, so the van der Waals forces become stronger, hence the boiling point increases from CH4 to SnH4. Alright, so this for the group 14, the boiling point of the molecule depends on the molecular size. Okay, and the van der Waals forces, of course. Okay. Okay, however, the case for group 15, 16, and 17 here, where is my mouse? So tiny. For group 15, 16, and 17 here, except for this NH3, H2O, and HF, there are hydrogen bonding, kan? So, sorry, for the hydrides of 15, 16, and 17, there are other hydrogen bonding. The other molecules inside the group doesn't have the hydrogen bonding. So these three molecules have a special case. Since they have the hydrogen bonding, their boiling point increase drastically compared to other molecules in their respective group. Okay, this is due to the presence of the hydrogen bonding in the molecule. Okay. However, after the for the other molecules after them, they all have the what we call it regular trend increasing, going down the group, except for this three element. Okay. Alright, so the increase in the boiling points for the hydrides of each period group is due to increasing strength, yes, of van der Waals forces as the molecular size increases. However, if we look at this H2O, HF, and AH3 group 16, group 17, and group 15, they suddenly have the highest among the other group. Padahal sepatutnya they should be lower, right? But since there is the presence of hydrogen bonding, that's why they has highest boiling point in their group. Okay. Now we need to compare between H2O, HF, and NH3. Which of these three has the highest boiling point? Okay, so the strength of hydrogen bonding is actually proportional to the polarity of the bond. So if we want to look at the bond, polarity of the bond, so we can see that actually, I'm looking for my pen. Where is my pen? Okay, that actually F is the has the highest electronegativity among them all and has the highest polarity among them all. However, the boiling point here, they increase in this one. H2O has the highest boiling point, followed by HF and H3. Why is that so? Why H2O suddenly has the highest boiling point? Why not HF? Okay, because H2O has higher boiling point than HF because it can form more intermolecular forces, hydrogen bond, compared to HF molecule. If you look here, okay, oxygen, oops, why is it like this? Okay. Alright, if we look at this, the oxygen, hydrogen. Okay. this can form hydrogen bond with the different water molecule. This also can form the hydrogen bond. Oh wow, Akbar. Why is this like this? Okay, this hydrogen can also form the hydrogen bond with the oxygen of another water molecule. And same goes to this. So that means that one water molecule can form up to 4 hydrogen bonding. So it's a lot. So when water can form more hydrogen bonding, that means that more and more and more energy is going to be needed to break the bond for that water to go into the gas phase. So it's exceptionally highest boiling point among HF. So when we compare HF and NH3, we are going to compare about the polarity since fluorine is much more polar than nitrogen. So that's why HF has the higher boiling point than NH3 because F is more electronegative than an atom. Okay, so F has stronger hydrogen bonding than NH3. Okay, so reminder, how to compare boiling point between two or more substances. So we need to prioritize whether the molecule can form hydrogen bond or not. If the molecule can form hydrogen bond, then it totally has the highest boiling point among the other molecules. And then if all the molecules cannot form hydrogen bond, okay, then we look at the molar mass. If there is a big difference in molar mass, then we use the London force dispersion as the factors that affect the boiling point. However, if the molar mass is almost the same, then we can check the presence of the dipole-dipole bond so that we can compare between the dipole-dipole forces. Okay. So yeah, this one I will not touch this. Okay, so now we are going to look at the relationship between the hydrogen bonding and the density of water. Okay, so you know that water can form up to 4 hydrogen bonding per one molecule. Okay, so given that water molecule is actually has what we call it, V shape, and when it forms the hydrogen bonding, it can form like a tetrahedral shape, right? Okay, as a result, the geometry arrangement of hydrogen bonding ni, bila it exists as a solid, which is ice, it exceptionally has an open hexagonal shaped crystal structure. Okay, it's big structure. So when water freeze, it will has an open space. Hence, we can say that the volume increases. So when the volume increases, the density decreases. Why? Okay, look at this. Density is equals to mass over volume. So when the volume increases, the density decreases, the mass increases. Oops, sorry. Okay, so this is the relationship. Okay, so that is why ice floats in water even though it's solid, because the shape of the ice has been hexagonally opened and like expand so that it can have bigger volume. So when this ice has bigger volume, then the density will become smaller, which will make the ice floats on water. Okay, like this. So like this. When water is cooled to a solid, the water molecules arrange themselves to form a tetrahedral arrangement in such a way to maximize the amount of hydrogen bond between them, resulting an open hexagonal structure. Okay, dia besar lagi volume dia. Okay, that's why dia lagi tidak tumpat. Okay. This arrangement of molecules has greater volume, is less dense than liquid water. Thus, water expands when frozen. Okay. So, yeah, hydrogen bond and water molecule can form up to 4 hydrogen bonding. That's why it has the ability to arrange tetrahedrali as well as open up the hexagonal space so that it has the high volume and low density. Okay. Alright. So now we want to look at the relationship between solubility and the intermolecular forces. Okay, it has the rule where light dissolves light. Something similar, the molecules with different, with the same, what we call it, characteristic, will tend to dissolve in the molecules with the same characteristic as them. Okay, the substance with similar types of intermolecular forces will dissolve in each other. Light dissolve light. Okay, for example, solid and HCl, dia ionic and dia ada dispersion force. So dia punya intermolecular forces dia adalah dispersion force. So water pun dia ada dispersion force. So dia ada similar intermolecular forces between them, make them enable them to dissolve together. Okay. Alright, so look at CCl4. So CCl4 is nonpolar and has dispersion force. And C6H6 also has nonpolar and has a dispersion force. So they both have the same intermolecular forces, making them able to dissolve with each other. So CCl4 will be able to dissolve in C6H6, which is the benzene. Okay, so let's look at H2O and CCl4. So H2O has a dipole-dipole force, dispersion force. But CCl4 has only the dispersion force. They don't have the same intermolecular forces between them. So CCl4 cannot dissolve in water. Okay. Alright, so let's look at the hydrogen bond in water and simple alcohol. Okay, so hydrogen bonding in water and alcohol are of similar type and strength, so they can substitute for one another. Okay, so methanol is soluble in water because it can form hydrogen bonding with water. Okay, so anything that can form hydrogen bond with water, dia soluble in water. Okay, so if you reminder, okay, alright, yeah, I think that's all for today. No, for today. For chapter 4.4, tak habis lagi. Okay, kira chapter 4.5 lagi after this. Okay, so let's go to chapter 4.5. We have chapter 4.5. For chapter 4.5 is about intramolecular forces, which is metallic bond. So since this is just a lecture and we don't really explain too much about this in this lecture, because your tutorial lecturer will teach you more about this later on. So let's look at 4.5 metallic bonding. So the learning outcomes at the end of the lesson, student inshallah should be able to explain the formation of metallic bond by using electron C model, relate the metallic bond to the properties of metal, explain the factors that affect the strength of metallic bond, and relate the boiling point and or melting point to the molecular structure, types of bonding, and intermolecular forces for elements in period 3, group 1, and group 17. So for today we are going to focus on the first three lah, because it's in the slide. Okay, the what we call it, the chapter, the last learning outcome. Your tutorial lecturer will explain more about it because it consists of more explanation. Okay, so this lecture is just the introduction on the surface. Okay, so let's look at what is meant by metallic bond. Okay, so metallic bond can be defined as the electrostatic forces between the positively charged metallic ions and the sea of the localized electron. So this we call it electron C model. Okay, so for example, this is what we call Mg2 plus, ni Mg2 plus, for example only, okay? So, the attractive forces, the electrostatic forces between this positively charged metallic ion and the sea of the localized electron around the metallic ion is the metallic bond. Okay. So look at that one, nucleus and initial electron, mobile sea of electron. So, in a metallic bond, metal's atoms can be imagined as an array of positive ions immersed in a sea of delocalized valence electron. Okay, if we look at this, Okay. Okay, and A plus has one valence electron. Okay. If we look at this, they said that, so if we can see that actually the valence electron, the C of the nucleus electron around the metal cation, actually they act as a glue, act as a glue to make sure that the cation, the metal cation stay together closely, to have like a bond between them. Padahal tak pun, dia macam like act as glue lah. Sebab apa? Because actually if the positively charged together, they like repel each other, right? So that's why the C of the nucleus electron, it acts as the glue to have the forces between them, so that what we call it, ada bond lah between them. Okay, quite between the atom in the molecule. Okay. So, oops. All right, yeah. So these nucleus electrons are not bound to individual atoms, and therefore they can serve to bind large amount of metal atoms together. They can move freely. They are the C of the nucleus electron. They don't have like specific atoms to serve. They are free to move. Okay, inside the space of the metal lah. Okay. Okay, so this are the properties of the metals. So as you can see, that metals are very shiny solids at room temperature with the characteristic of very high melting points and density. So these are the 4 properties of metals that you have to know. First, malleability. So malleability, is it correct how I pronounce it? I don't know. So malleability is the ability of a metal to be hammered into shapes, able to deform without breaking. So like when like for example, we have piece of metal. So when we fold the metal, we knock it and it will form a different shape. It has the ability to form into other different shape without being breaking up. Okay, dia tak patah ke apa ke tak. Dia boleh lipat-lipat, dia boleh ubah-ubah bentuk. Alright. Next, ductility is the ability of a metal to be drawn into wire. So metal have the ability to be drawn into wire. That is one of the properties. And then next, metal is also a good heat conductor and electrical conductors. Why? So because they have valence electron that can move freely around the space. Okay, but how actually this valence electron that can freely move help the metal to conduct heat and electric? Okay, for electric conductor, metals have the freely moving valence electron among the metal cation. So this C of delocalized electron will actually act as a charge carrier to bring the charge from one part to another part of the metal. So that's why metal can conduct electric. Same goes to heat. So electron can transfer the heat from the hotter part of the metal to the cooler part of the metal. So they can transfer heat. That's why metal both is a good heat conductor and electrical conductor. Okay. Next, the relationship between the strength of metallic bond with the melting point and boiling point. So actually the melting point of a metal indicate the strength in its metallic bonding. Okay. So the strength of metallic bonding is inversely proportional to number of valence electron and inversely proportional to the size of metal cations actually. Okay, so when the number of valence electron increases, the strength of metallic bond increases, and when the size of metal cation decreases, strength of metallic bond also increases. Okay. The reason why the size play an important role in what we call it, in measuring the strength of metallic bond is because the smaller the metal cation, the closer the distance between the metal cation and the electron, making the bond form much more stronger. Okay, so Look at this between period 2, period 3. Sodium in period period 3, I'm sorry. Okay. Alright. So, if we can see that kalau kita compare the valence electron of Na, magnesium, why is it like this? And aluminium, sodium has 1 valence electron, magnesium has 2, and aluminium has 3 valence electron. So, aluminium has the highest. So, that's why dia punya metallic bond is strongest. Sodium has the lowest number of valence electron, that's why it has the weakest among the element in period 3 lah. Okay, so this is why when the valence electron increases, the strength of metallic bond increases, hence the melting point and the boiling point also increases. So the more number of, so bear in your mind, okay, the more number of valence electron, the stronger the metallic bond. The smaller the size of metal cation, the stronger the strength of metallic bond. Okay. So these are the groups lah. Dia susun ikut table lah to show how actually the boiling point increases. Okay, how many degrees Celsius for aluminium to be boiled? Wow, 2,450 degrees Celsius. Really, really high boiling point here because aluminium has a very strong metallic bond because of the C of the localized electron. Alright, so I think that's all for this part of video, chapter 4. We have finished chapter 4. I will make a second video to explain about chapter 5 after this. Alright, thank you. Assalamualaikum.